Welcome to part B of lecture 23. During this part, I'll be looking at the Sturm-Liouville problem. This is a problem in ODEs. However, it plays such an important role in solving PDEs by separation of variables and solving various classical quantum mechanical problems that I thought it was worthwhile at least looking at the results carefully and spending at least a lecture or a lecture and a half on doing so. Okay, we encountered a number of Sturm-Liouville problems when we separated the spatial part of the wave equation and the ellipse. In particular, we found that you made Matei's equation, and I just wanted to highlight the main parts of the Sturm-Liouville theory that makes finding solutions easy. Okay, so the Sturm-Liouville problem is a problem that was explored by Sturm and Liouville during the 1800s. And what it basically was a series of techniques and results for solving a real second-order linear differential equation for yx of a particular form. And that form is written like this. So you have d dx of some function of x multiplied by the derivative of y with respect to x. So effectively, this bracket contains a second derivative of y, plus another potential function, plus lambda, which is a constant, but it's not a constant that's fixed a priori. It is actually fixed by finding the solution of the problem, times another function omega of x, and this they often call the weighting function, which the reason for which will become obvious later, multiplied by y of x, which is the unknown that you're looking for. Okay, and you're going to be solving it on a specific domain. X is an element of A and B, and the coefficient functions basically have these properties. So it can be any function of x and q and w, but w of x is assumed to be greater than 0. These functions are known, actually help define the problem, so they're known ahead of time. Lambda is a constant, but it is not a given constant. It's a constant that you're going to be determining, because it turns out that the way that we specify this problem with this differential operator, in addition to the boundary conditions we're going to specify, it's not always possible to find a solution for any lambda. Okay, now the key thing that separates the Sturm-Liouville problem from finding a problem from an ordinary second-order linear differential equation for y is the way in which we specify boundary conditions. So if you think about the Sturm-Liouville problem or second order problem, what you usually do is you specify the boundary conditions at a particular point. And if it's a second order problem, you specify both the initial value as well as the first derivative. And then since it's a second order problem, all higher derivatives are then fixed by your differential equation. With a Sturm-Liouville problem, it's a different kind of problem. And it's a different kind of problem that arises a lot whenever you do separation of variables or whenever you do solve quantum mechanical problems. So what makes this problem different is the way in which you specify boundary conditions. So instead of giving all the information at a particular point, you separate the boundary conditions. You give some information at one point and some other information at another point. So we basically say, instead of specifying both y and y prime at point A and nothing else, what you do in a Sturm-Liouville problem is you specify some combination of y and y prime at point A and some combination of y and y prime at point B, but only one piece of information is given at each part of the domain. So for example, you're at A. If alpha 2 is equal to 0, you've basically specified that ya is going to be 0. If alpha 1 is equal to 0, you specify that the first derivative of y is 0, but the value of y itself is free. And similarly at point B. Okay, and so now to actually give you the first idea of what the results that I'm going to summarize now and prove in part during this first part and then more of the results during the second part of the lecture is, suppose we look at the very, very simple example just to illustrate why this is a different kind of problem from solving ordinary second order differential equation starting at a particular point. So suppose you look at the special case when P of x is 1, Q of x is in fact 0, and W of x is 1. Okay, so you basically have the second derivative of y is equals to lambda times y. So we already solved that. That was the same equation as what we had for our time dependence, and the solution was a whole bunch of sine and cosine functions. And also, for argument's sake, let's simply suppose that alpha 2 is equals to 0. In other words, that at point A, y is specified, y of A is equals to 0, and point B is also, we said we choose the case where beta 2 is equals to 0, so y of B is equals to 0. Okay, and now to illustrate the situation, and why in fact you cannot have it for every lambda. Let's start at point A. The only information we're given at point A is that the value of at A is 0. The other condition is we want is that the value at B is 0. Okay, but we haven't completely specified the solution for the differential equation. So at A, one way of solving the problem would be, let us try a whole bunch of initial derivatives, a whole bunch of gradients that we shoot the solution away with, and then we integrate this equation. Okay, and you can now see that suppose we start with lambda, a certain lambda. Okay, there is just, not every lambda would actually get you so that the solution is at reaches B. So suppose you start with a certain low gradient that you shoot the thing out with like that. What will happen is you'll go out, you'll integrate it, you'll have a sinusoid, but only for the right wave, for the right lambda will you actually have the sinusoid so that it equals 0 at B again. Similarly, you can then increase the initial gradient that you shoot it with a steeper one. Okay, and after a while it will no longer be possible for you to make a single hump and get to B. As it becomes steeper, you'll have to take a sinusoid, but the lambda will have to take a different value. In fact, you'd have to get to the point where the lambda intersects with your x-axis at least once before it gets to B. Okay, and that would also be a discrete value of lambda. That is different from the one hump solution. And then suppose you increase the initial gradient even further, then you can no longer get a two hump solution. You would have to go and you'd have to find the solution with a particular lambda that will allow you to transverse the x-axis twice before you get there. Okay, increase the initial gradient further, and you now, in order to satisfy this equation, which only can give you sinusoids or cosine functions, you're going to have to get another solution where you have lambda n that intersects the axis several times. Okay, and this type of solution where for your given equation with given fixed functions and the separated boundary conditions, this property that you can get several solutions for only you discrete values of lambda that have different types of zeros is generic for any one of these functions. It happens, the actual form of the function changes, but the fact that it has these zeros that crosses the x-axis at several points before it goes back to the boundary condition specified on the other side, that's a property that's robust, and that is what Sturm-Liouville theory basically is about. Okay, so from the equations we derived for the elliptic problem, you can see that this property where you actually have this idea that you're solving the second order equation with the two boundary conditions at two different spots is going to lead to a specific choice of those constants that we're actually entering into those equations. Okay, and I'll make that explicit when I actually solve the problem. But for now, all I want to do is actually look at this completely general case, because it allows you to actually solve or look at several second order or almost any second order problem that arises from separation of variables. So all I want to do now is simply highlight the main results of the Sturm-Liouville theory in the slide, and then the next slide I'm going to start giving some of the basic ideas towards the proof. Okay, so the main results are, if P and W are greater than 0, so if P of X and W of X are greater than 0, and P prime, Q and W, so these functions, so this one is the function and its first derivative is continuous here, Q and W are continuous on the interval AB. Okay, then the eigenvalues are functions are real and they're ordered, just as here these different lambdas for which you actually get a solution that goes back, or in fact, in some way of thinking about it, is you actually manage to set the frequency of your sinusoid in such a way that the 0 occurs at B. And that there are several frequencies. The more nodes you have, the higher the frequency basically goes. That thing is robust, and it's actually a property of all these type of equations. So this is the first main result of the Sturm-Liouville theory, is that the eigenvalues lambda I are real and they can be ordered. In other words, you have the eigenvalue 1, which is less than the eigenvalue 2, all the way up to infinity. And these, for each eigenvalue, right, n, so there's a unique eigenfunction, which basically corresponds in this example to a sinusoid, psi n of x, and it has exactly n minus 1 zeros. Okay, so lambda 1, which is the solution I haven't plotted, which is just one hump going there, has no zeros. Lambda 2, which is this sinusoid that crosses over there, has two humps, has 1 0. Lambda 3, which is this psi n sinusoid, has the 2 zeros, etc., etc. Okay, so this property that I sort of gave with a very simple example of the sine function is actually a property that appears in all the solutions of these equations. Okay, and this particular solution is known as the nth fundamental solution. Another thing that is particularly useful, because remember I said in the previous example that we're actually going to find in those expansion values, and I didn't say how. There's actually a theory that results from the Sturm-Liouville theory that makes that possible. And this is the first idea that sort of leads to that. So the normalized eigenfunction, okay, like lambda n of x, they form an orthonormal basis under the inner product that's defined in this way. And this is why we call the weighting functions. So one way you can basically view these two solutions like this, in this case, like let's say sine of nx and sine of mx, as two fundamental solutions to this eigenvalue problem. And you can define an inner product between them. And the way you define the inner product is simply the one function multiplied by the other function multiplied by this weighting function that's in your actual problem itself, and you integrate it over the whole domain. And the theory basically says that unless the eigenvalues are the same, okay, this integral basically vanishes. So you basically have delta mn, and because it's a linear thing, you can actually rescale any eigenfunction, and we're basically assuming that we've rescaled yn of x, so that this integral of when n is equals to m is just equals to 1. Okay, so there's an orthonormal property with solutions of the Sturm-Liouville problem, and that an orthonormal basis actually allows you formally and rigorously to find an expansion of any function that obeys the same boundary conditions on this domain. So you can start seeing why this type of result is powerful when we actually want to expand the solution of the PDE on that domain, just as we used it when we looked at the Green's function for the heat equation. So what I'm going to do in the next slide is simply start deriving some of these results or some of the lemmas that lead to these results, and I'll go on during the next lecture to sort of make a list of all those results. So the first step is, let's define a linear operator that was basically inspired by that Sturm-Liouville problem. And let us say that the linear operator is equals to 1 over omega x, which is the weighting function, times d dx p of x ddx, okay, plus q of x, and then we apply that linear operator to some other function. And we're going to denote our eigenvalue problem simply as the problem where the linear operator applied to y of x plus lambda of y is equals to 0. In other words, we want the eigenvalue problem is the solutions where we simply have the linear operator applied to y that just actually returns a rescaled version of y. Okay, and we're also going to denote the boundary conditions as, and I'm going to call them BC, as the one boundary condition at A and the other boundary condition at B. So now I want to do is look at what the various things, why the problem is constructed in this way, and why the results that you can have these orthogonal basis functions that have these various nodes can be so cleanly obtained. So the first property comes from the linear operator only, and that property is for any function that maps the interval AB to the real values, the following is true. Suppose you apply the linear operator to f, and you take the inner product with g, and that inner product is simply this thing that we defined in the previous lecture. In other words, the inner product of two, on the previous slide, the inner product of two functions is simply the integral from A over the interval of your weighting function multiplied by the two elements that you're taking the inner product of. Okay, so the first property is the inner product of L applied to F minus the inner product of F applied to L is simply equals to a boundary term evaluated on the boundaries. And it's just another way, it's sort of a Green's-like property that we've been using previously to write down our Green's functions, but this is just sort of the ODE version. This type of property is also possible because L, I don't know if you had a course in calculus of variation, L is a self-adjoint operator, and this is just sort of saying it. Okay, so I just want to prove this property. So let's start and just write it down. So L of f comma g is simply this integral, as I've mentioned. And what we're going to do now is simply write out the effect of the operators. So L2 goes in there. So it's basically gx times wx, but that goes out with that wx, times ddx of p of x ddx plus q of x multiplied by f of x. Okay. And what we're going to do next is we're going to integrate by parts twice. And what we basically going to do while we do that is we're going to shift these differential operators onto the function g. So the first step is to take this ddx and take it outside. So you have ddx of g of x multiplied by everything inside. And then you've got to subtract the part that is different. Okay, so you basically have ddx of gp df dx minus dg dx of p df dx, and then the second term is just there's no differential operator, so it's just remains the same. Okay, so there's the first integration by parts. The second integration by parts is to basically shift the derivative here of f onto this thing. Okay. And so what you have is here the boundary terms remain the same. So the second one is basically saying ddx, which will give you another boundary term of f of dg dx dp. And what you want to do now is add back the extra part. So you want to add back the derivative of ddx of p dg dx. Okay, so there we have it. Plus this final part over here that's left unchanged. And so you've basically got the result yet. These first two, if you look at them carefully, are just boundary terms, and p multiplies both of them. So that's basically your boundary term over here. So that's PGF prime minus FG prime evaluated at the two boundaries. Okay, so that term is fine. The second term, if you look at it carefully, it is actually exactly the same as this top term, just with F and G switched. So it's actually, the second term is simply f of x, w of x, L of f of g of x, L applied to g of x dx, which is just the inner product of f comma lg. Okay, so that's the first term, as I said, and the second term, okay, which immediately gives you a result up here. Oops. Okay, so that's sufficient to prove the result. And this result is, as I've said, only a property of your linear operator. So let's now see what happens if, in addition, we look at a function, a general function that obeys only the boundary conditions. Okay, remember, when we derived this lemma, we did not say that f and g were an eigenfunction of the solution. We simply said that f and g are any function that map the interval to the real values. But now let's restrict f and g to being any function that obeys the boundary conditions. And this is like the type of solutions we seek when we do separation of variables, because we simply want functions that obey the boundary conditions and then obey the wave equation in the middle. Okay, so we're going to say for all f and g on that map the interval to the real numbers and obey the boundary conditions, we simply have that the specialized version of the result where the right-hand side vanishes. And so all we have to do now to prove this result is simply to prove that this thing vanishes, and it's almost just a direct definition of the boundary conditions. Let's examine what happens at x equals to a. So at x equals to a, let us assume that if we have the case where alpha 1 is equals to 0, you immediately have that f derivative is equals to 0 and g derivative is equals to 0. So then this result is, this thing is 0 at a. And if you have the case where alpha 1 is not equals to 0, you can divide by it. So then you can have that y is equals to minus alpha 2 over alpha y on y prime, or in this case, g is equals to alpha 2 over alpha 1 minus g prime times f. And here we have that f is equal, or minus f is equals to minus alpha 2 over alpha 1 times g prime. And this thing vanishes or cancels, so it's 0. Okay, and the same argument you can go through at x equals to b. So simply by looking at functions that satisfy the boundary conditions, you have from lemma 1, with the fact that this thing is 0 at both points, that the above result holds. Okay, so that's a property of both L and your boundary conditions. So now let's go one step further, and we actually start looking at eigenvalues of the solution, or an eigensolutions of this problem. And let's let lambda n be a specific value lambda for which you can actually solve that problem, and let the eigenvalue associated with that lambda be yn of x. Okay, and that's a solution basically of SL over there. If we have that, and we have the fact that, which is part of the problem basically, or part of the definition of your eigenvalue and your eigensolution, that it obeys the boundary conditions, then we have lemma 3, which is basically the following is true. Okay, that lambda, the eigenvalue of m minus the eigenvalue of n, multiplied by the inner product of the two fundamental solutions is equals to 0. And this is the first step in the proof of property C, where if m and n, or the two eigenvalues, are different, this thing is non-zero, it basically proves orthogonality of your of your fundamental solutions given the inner product that's defined in this way. without L. Basically, given the inner product that's defined as integral from A to B of your weighting function multiplying the other, basically these two functions. Okay, so that proves orthogonality, and it's easy to prove that things are orthonormal because you just, if rescale an individual function so that this inner product of yn with itself is equals to 1. So let's just quickly prove this before we conclude this lecture. So let yn of x and ym of x both satisfy this condition, so you can just write it out. Okay, so the linear operator applied to yn is simply a rescaled version of itself, and the linear operator applied to ym is simply a rescaled version of itself. And we also know that it obeys the boundary conditions. Therefore, by lemma 2 over here, okay, we have that these two are equals to 0, with a specific case where f and g are now your fundamental solutions. But you know more about fundamental solutions than just arbitrary functions, because you know that L of yn is simply equals to minus lambda n of yn. Okay, and minus lambda is just a constant, so you can take it outside of the inner product. So what stands here is simply minus lambda n yn comma ym. And similarly over here, this L, you can simply replace it with minus lambda. Sorry, there should be an m over there. So that should be, so this inner product can be minus lambda m yn ym. And if we do that, we simply get the expression given above here. So we've concluded the proof. Okay, so we've basically proven the first step of property C. And during the next lecture, I'll start looking at the other properties as well as how you actually expand an arbitrary function f in terms of these basis functions. Okay, so that concludes lecture 23. I will be back with more properties of the Sturm-Liouville problem in the next lecture, and then ultimately return to solving our separation of variables on the ellipse. Thank you very much.